Hello everyone. For this primer video segment, we're going to be talking a little bit about recursion. So recursion is something that tends to scare people a bit. It's a tough concept, and it can get a little bit difficult to follow at times. That being said, once you've got it, once you've really got it down, you unlock a new way of thinking about things that is quite powerful. Not only in programming, but it's just a cool new way to experience, you know, this recursive idea. It's an interesting concept. Um, so let's today go over recursion just a little bit. Take a look at a simple but useful example of recursion. Um, and in doing so, let's hope that we can move towards understanding the concept behind recursion a little better and hopefully be able to think recursively. It's like thinking with portals. Um, so our goal here is we're going to create a tree. We're going to use structures to create the tree. It's going to look like this. And we're going to use recursion to print every full sentence combination. So for example, our root of the tree is hello. This could be hello world. This could be hello, my name is Max, or a secret. Or it could be hello, CS252 students, TAs, or professors. So we have these different options, but we can't do something that doesn't align with the tree. We have to use only the words in the tree, and we can only do things like we couldn't do hello, my name is world. That doesn't follow the tree. So we have this tree kind of describing these different possible sentences, which is kind of useful to us. And we want to just print out every full sentence combination that's possible here. This, of course, is going to be equal to the number of leaf nodes, so 1, 2, 3, 4, 5, 6. We're going to do this with a structure. There are better written structures, but this one is mine. And this one, this is C++, by the way, so we do have a function in here. Worth noting again, cat over there. Worth noting again that structures in C++ are basically the same as objects, except that default member variables are private or public in structures versus private in objects. But anyways, we have the struct. It's got data, and it's got 3 possible children, C1, C2, and C3. And anytime it doesn't have one of these, it's going to be assumed to be null. So a null is going to be no children. We also have this constructor. Worth noting here, a cool feature of C++ is we can actually have default arguments. So in this case, the only required argument here is data, that string that's going to be our word in the sentence. And all these others, if we don't put anything in there, it's just going to assume them to be null. This is something which, if you program Python, you use this a lot probably. But it's also a useful thing here. I've also typed def this just to make my life easier for a thing we'll have in a moment. There's a cat causing problems over there. So yeah, we've got this print all sentences. We'll look back at that in a second, delete tree. But our main logic for this is we're going to create our tree. We're going to print, I'm going to create a string with this and then print that string of all of our sentences, and then we'll delete the tree to clean up. Never forget to delete, especially when you new to all of these. So this notation may look like the worst thing in the world, and it kind of is. I'd probably do it differently in real code, but it gets the idea here that we're almost in a functional way creating this tree. We're saying our root here is hello. One of its children is world, and that doesn't have any of its own children, so those are all null. One of them is my, which also has its own children. That'd go down to name is Max or a secret. And our other child here is CS252, which has its own children, students, TAs, and professors. So as much as this looks like garbage, it does the job. It is effectively creating this tree in a sort of functional format. And as much as it looks kind of like garbage, it is pretty concise at the same time. It builds the tree in a fairly intuitive way. But once we have this, we now have a pointer to our root node. We want to put that into our print all sentences recursive function here. Now, print all sentences also has one of these default variables where we have a prefix that we're giving it that's going to be what the string has so far, and the node. First thing we do is we want to have a base case. It's always good to start with the base case because then the recursion part's usually a lot easier to think about. In this case, we can say if everything's null, if all of the children are null, we know we're at the leaf node. There's no children. If that's the case, all we have to do is the string for this leaf node is going to be whatever the prefix is, whatever has come before the node, plus the data in the node, and then we can put a new line in. So that's really easy. That's our base case. Each leaf is creating the sentence in the end. The recursion case can be a bit harder. First of all, we know we are somewhere in this tree. Could be at the very start, could be at the very end. Well, actually can't be at the very end. Could be anywhere but the very end. And we have a prefix. That prefix is going to be whatever has words have already come before. So what we can do is we create this aggregator. This is going to be the aggregation of all of our strings. And we are going to, for each child, check if it's not null. And if it's not null, we are going to add its version of print all sense to the aggregator. Now, quick quiz question. How many lines is this returning? Bit of a trick question. We don't know how many lines it's going to return. It's going to return at least one line. We know that because it's going to eventually get down to a leaf node, and when it gets to a leaf node, it's going to be doing this. But how many lines is going to depend on how many leaf nodes it gets to. If we are right here in the tree at CS252, it's going to return 3 different lines. One for the student leaf node, one for the TA's leaf node, and one for the professor's leaf node. If we are at name, even though we have a few different nodes and they're at different levels even, we know we're going to be returning 2 lines because there's only 2 leaf nodes in this subtree. So we don't really need to worry about that too much because how we have this aggregator set up, it's just going to add in lines as we go. And then our new prefix, it's worth noting, we're going to set our new prefix to be whatever our prefix was already, plus our new word. So we're adding in our new word. And then our node, we're just going down to the next node. We're going down to that C1 as being our next node. And then at the end, we can return aggregate. So how this will work then, start on our tree. We start with this and an empty prefix. We check if it's a leaf. It's not. So then we check, is there a child here? There is. That one is a leaf. So we can return into our aggregator that string, a hello world string. We have this one. We're saying my, not a leaf node. Name, not a leaf node, is not a leaf node. Max is a leaf node. Now it's going to turn hello, my name is Max to the aggregator, or to this one's aggregator, which isn't going to return it yet because it still has this one to go. So for this one, it'll say A, not a leaf node, secret, that's a leaf node. So we return that to this aggregator, returns that to this aggregator, and now we have aggregated 2 lines. There are no children left. The C3 does not exist here. So we can return that to name, return that to my, and return that to hello. Now we have hello world, hello my name is Max, and hello my name is a secret. Same thing happens here with 252. But let's move on now to deletion. Now you see in this case, importantly, we have this prefix and we are going down to the bottom of the tree before we build up again. It depends on what you're doing with the recursion, but this can be a pretty good way of doing it where we aren't actually adding things until we get all the way to the bottom of the tree. And delete is very similar in this way. So for delete, notice we actually recurse before we delete. So we are going to, it's going to be a depth first approach, sort of. We start with hello. We're not going to delete hello right away. We're going to recurse down to world, my, and 252. Or more specifically, we'll go down to world. That's going to get deleted. We'll go down to my name is Max. This gets deleted. A secret. This gets deleted. This gets deleted. Delete, delete, delete. 252. Delete, delete, delete. Delete, delete. So it's going to go down first and then eat its way up. In this tree structure, like I've got a tree here. The great thing about recursion is you can almost always think of it like a tree structure. That's really, really useful to us because later in the class when we do things that are very recursion heavy, that will be very difficult to plot out in your head. You can fall back on this tree structure. And I wouldn't do this with like ASCII text like I did here. I would take an actual piece of paper and draw out the tree structure that you're working with, because that will give you a visual idea of how this recursion works, and it'll make life a lot easier for you in the long run. I would say that's it, but I think we have to run this program at least once. That'd be very sad if we didn't. Tree. So there we go. Hello world. Hello, my name is Max. Hello, my name is a secret. And the 252 ones. So good stuff. I don't think I have anything else here. Just remember, recursion is something that it's worth putting the time into, not just for this class, but to unlock a new way of thinking about functionality. That's all I have for you now. Peace.